So I'm Tim Searchinger, if you don't know me, but today is we have the distinct honor of being able to hear Lyndon Estes, our own Lyndon Estes, who's a associate research scholar in both STEP and the civil engineering program. Lyndon is one of the people I admire most. His publications are in part because he, like me, is interested in this intersection between conservation and agriculture. He started actually in the conservation world as a wildlife manager in South Africa well before he went into academia, and actually has real honest-to-God interactive experience, unlike most of us, including me, who basically seen animals from a distance only. His papers deal with traditional biodiversity and conservation subjects. They deal with crop modeling. They deal with the impacts of climate change. They deal with trade-offs. And above all, they deal with wet savannas or savannas. Lyndon is, like me, a savanna lover, not really a forest lover. And savannas are the ecosystem that gets most shortchanged in the world today. What I particularly admire about Lyndon is that he's a real scientist. In a lot of our fields, there's a lot of desire for conclusions and often shoddy modeling and shoddy data that goes to support those, and even things that get published sometimes in very fancy journals are published there because their result is exciting, not because they're really super rigorous. And what I love about Lyndon the most is he is a rigor kind of guy. He does not let ideology or belief get in the way of what he really, what he wants to believe, get in the way of what he actually thinks is true. And he combines really detailed methodological efforts with thinking about big subjects. So I think today he's going to convey that. He's going to talk about some very detailed subjects that he works on, but remember that they all add up to dealing with the most critical subjects that at least many of us care about, which are basically how do we maintain some kind of decent conservation in the world, maintain carbon, and yet do it in the context of expanding agriculture.
Thank you. I have to pay you to be my publicist now. I appreciate that. And since you gave my talk, do you guys have any questions? No. Anyway, so I'll talk to you today about some of the work that I do. Basically, the overarching objective of my research is to figure out how we can dramatically lower agriculture's environmental costs, much more than our conventional practices allow for right now. And the work of, you've heard from Tim and others like David, that we have a massive challenge facing us in the next few decades, that we have to roughly double the amount of food that we currently produce. We also know that agriculture is probably one of the greatest disruptors of our planetary support systems. It's the largest driver of terrestrial biodiversity loss. It's also one of the major drivers of climate change. So if we want to avoid nasty environmental surprises, as we move towards this goal of trying to double our food production, we have to really change our current agricultural practices. And so I'm going to talk today about one approach that we've found that might have some promise for greatly lowering the environmental cost of new agricultural developments. But this is mostly a talk about data, as Tim hinted at, because policies that are going to get us to dramatically lowering environmental costs of agriculture are, I would argue, unusually dependent on data quality. And that's, I'll get to those reasons. Can you guys see this? It seems like the lights are washing that out. Okay. All right. So, I'll describe what's on there.
Turn off these lights.
So, with respect to thinking about agriculture's, the types of areas in which agriculture causes environmental impacts and where you might target policies, I find it helpful to create 3 bins or 3 rough categories. You might think of how much new cropland is going to be needed and where that new cropland is going to come. That's a major factor that will relate to how much environmental impact agriculture has. Think about what we do on current cropland, our practices on current cropland. And there are many factors to think about, such as how much can you boost yields and therefore avoid the need for new cropland? How do we respond to climate change with our agricultural practice? Can we sustain our current agricultural practice? There's also another category which I'm interested in, which I think is going to be increasingly important. It's important in places like New Jersey, certainly, which is what other land uses might compete with agriculture. So if you think of it within a New Jersey context, where we have suburbs replacing cropland, that directly affects the environmental impacts that agriculture has, say, by perhaps causing new cropland that needs to be created elsewhere. Anyway, my work mostly focuses on these two, and the subject I'm talking about today relates to the new cropland aspect, which I think is going to be perhaps one of the most important things we need to get under control, the environmental impacts of that in the next few decades. And the reason for that is because of what's going to happen in Africa. A number of you have probably heard me say this multiple times already, but I'll reiterate it here for your benefit. But Africa is going to have the largest number of new people this century. It's going to double its population by 2050 and perhaps quadruple by the end of the century. It has some of the fastest growing economies on Earth. You add those two factors together and there's going to be a lot more demand for food. There's roughly probably a quintupling or a tripling to quintupling of food demand by the middle of the century. And then you also have the fact that Africa has got 1/3 of the world's remaining potential cropland. A lot of that is within Africa's Savannah region. So there is going to be a lot of new cropland being developed in Africa this century. Tim, Dan, and I wrote a paper that we published last year in which we estimated that we're probably going to need about 140 million hectares of new cropland to meet the demand, the food demand by 2050. And that's under fairly optimistic yield growth scenarios. So what can we do to hold down the cost of that new cropland? That's important because this is going to happen in an area that has substantial stores of carbon and also some of the world's most important areas of biodiversity. So it's got the potential to cause a lot of ecological damage. So that's why I'm focusing on this question about how to minimize the cost of new cropland. Now, this is where the data comes in. The data quality issue comes in. To be able to find policies that hold down the impact of new cropland, you have to be able to answer 2 questions fairly accurately. You have to be able to first identify where the areas are that allow you to meet agricultural needs but at much lower environmental cost. You have to do that with fairly high spatial accuracy. You also have to be able to figure out how much of that there is. But the first question, I think, is superior to the second one. That question is critical. That's the question that we are actually least able to answer because we don't currently have the data that allow us to do that. And so I'm going to now talk about, I'm going to emphasize the importance of this question within the context of the new approach that we've developed that might allow us to identify lower environmental impact new cropland. And I'll start by illustrating the concept of how that's achieved with some dummy data, some toy data that I made up here. So the way we might achieve lower impact cropland expansion basically is a matter of landscape scale. So take an imaginary landscape. It's just arbitrary data that I generate, in which you have a potential yield for a crop on the left and a measure of ecological cost on the right. Let's imagine that's carbon density. So that's the amount of carbon that's lost, some measure of the amount of carbon that will be lost when you convert the land for new crop. What you can see by looking at these maps is that there's some correlation between those values. Let's plot that side by side with ecological cost on the x-axis and potential yield on the y-axis. And you see that there's a correlation. So basically, this is something that happens. This is roughly what you get in nature. The areas that tend to be higher yielding for growing crops also tend to be of higher ecological value. They have more carbon, they have higher biodiversity. But there are differences. You have some areas which actually might have very high potential for growing crops, but they're actually fairly low in terms of their ecological cost, and vice versa. If we can identify areas like this that are high value, low cost, and target those areas preferentially for agricultural development, then we can actually hold down the environmental cost of new agricultural development quite substantially. So that ends up giving you an approach like this, where you can rank, you basically reframe this as a matter of efficiency. You divide the ecological cost by the potential crop yield, and that gives you a basis for ranking the landscape based on its ecological efficiency. So you want the areas that are basically have a low ratio, a low value. That means they have a low impact relative to their yield. High denominator, low numerator. And then you rank the landscape according to that, and you end up with something that looks like this. It just looks like a bunch of random colors, but basically the blue and green are the areas you would preferentially develop. And you convert, by converting areas from the most ecologically efficient to the least, hopefully you reach your production targets before you do too much damage, or you have much lower damage. And so here's a map of what converting the top 25% in terms of the ecological efficiency of that landscape looks like. So we've developed a model as part of Tim's NORAD project focused on Zambia that is basically an enhanced version of this concept. It takes this concept of efficiency and builds a model. And it actually builds, it was inspired by an approach that Leon Pinko developed for looking at oil palm development in Southeast Asia. Our concept is slightly different because we incorporate the idea of efficiency, and we also do it in a way that we allow stakeholders to look at the value of minimizing different costs of farming. So basically the model has an assumption that given production targets for multiple different crop types, you identify new farmland while balancing amongst 4 potentially competing costs. 2 of them relate to the agricultural potential of the land. One cost is total land area, which is the reciprocal of yield. So in other words, if you convert the least amount of land, you are actually selecting the areas with the highest yield potential to get to your target. You also look at the production costs for growing that crop per ton of yield. And now you have 2 ecological costs: carbon loss per ton of yield and biodiversity loss per ton of yield. And crucially, the preferences for the costs can vary. You can place more or less weight on each of those objectives. And the idea is that people with different objectives for how they'd like to use the land can basically evaluate the effect of changing these weights and come up to a compromise solution. So that's a novelty of this model, and I have to give credit. A lot of this was done by an undergraduate. Marcus Spiegel developed a lot of the logic that goes into designing this model so that it can take varying weights and come up with an optimal solution for any given combination of weights. So we've developed a proof of concept for Zambia for the NORAD project, and we have a paper coming out on it in a couple months. But what we're trying to do right now is turn this into an operational decision support tool that looks at agricultural developments in Zambia and Tanzania. So I just want to run through the model very quickly. These are some of the major inputs that we have to develop for it. This is potential crop yields for maize and soybean, which are 2 of the most important crops for Zambia. We're looking at areas that are not currently farmed and which are not currently protected, as being areas that are candidates for agricultural expansion. So we mask out Zambia's protected areas, and we look at, and you can't see it, but we mask out its existing cropland, and then we look at the potential yields in the surrounding areas. Our measure of production costs are basically the amount of time it takes you to transport, say, 20 tons of a crop to the nearest city, the nearest major town in Zambia. That's a very rough proxy for other input costs for agriculture. And that's all we have at the moment, so it's what we're using for our proof of concept. And here's our 2 ecological cost measures, the layers that go into that. That's the amount of vegetative plus soil carbon that will be lost when you convert the land to new cropland. And this is a measure of biodiversity value, which is based on the relative rarity of vegetation types in Zambia, how protected those vegetation types are, and how intact they are. So it's a hybrid measure of biodiversity value that is unitless. It goes from 0, which is least value, up to 1. And again, we're only looking at areas outside of protected areas. Okay, so what the model does is it allows you, like I said, to value the variation in how much preference you have for minimizing any one of those cost objectives. All right, so these 4 maps show the model outputs that result for the extremes of each of those cost objectives. So the top left map is what happens when you care only about maximizing your yield. The top right is when you care only about minimizing your carbon loss, minimizing biodiversity loss here, and minimizing transportation costs. And the different colors are showing the areas that are identified as being the best under those objectives for growing maize in orange and soybean in red. And what you can see is that under these extreme measures, there's a fair bit of difference. Maize is mostly being developed there if you care only about yields, and soybean up here. If you care only about carbon, it's all the way, soybeans all the way over here, and maize is down here. So this gives you some sense of how those preferences might vary where you choose to develop new cropland. Interestingly, I want to highlight that if you look at minimizing biodiversity loss and carbon loss, and to a certain extent transport costs, there's actually a lot of overlap in the areas that are selected, which is actually a feature of the data set. Basically, you're trying to avoid the areas of highest carbon or biodiversity impact or cost, and those areas the areas that are highest value tend to be furthest away from roads. And this is where you're basically picking the areas where the biodiversity impacts and the carbon losses happen. If you're trying to minimize the loss of those things because you've already lost a lot of the carbon and biodiversity near roads. Here's a case where you can actually evaluate different levels of compromise between those 4 objectives. The top 4 maps, I won't belabor this too much, but it basically happens when a person, say for instance, who cares only about maximizing yield, is making decisions but's willing to pay 5% more than their lowest cost in order to compromise with other people. So they're basically willing to give up 5% of the yield value that they would otherwise achieve in order to allow carbon, biodiversity, and transportation. People care about those other objectives to get a bit as well. And this is the case when you compromise equally across all 4 objectives. Again, just to highlight the features here, you get a case where, interestingly, most of these solutions, with some variability, tend to coalesce around road infrastructure, which makes a lot of sense. And that's basically a feature of the underlying data set. So perhaps the real value is here, though, in the model, is where you can blast through, you can evaluate the actual cost of those land use decisions in objective terms. So this is the value, this is the cost of each of those maps above, they're color-coded. So basically the purple map is the equal compromise one, the red map is when the yield person gives up 5%. So you can evaluate their cost in each of the 4 major cost dimensions. This is the amount of total land converted, so the inverse of the yield potential. This is how much carbon is lost, how much biodiversity is lost, and how much transportation cost is incurred. And the gray bars show you the range between the best case scenario and the worst case scenario. And the best case in each case is when you put 100% of the weight on just that objective. And the worst case usually results from when you care only about maximizing yield. The nice thing about this is that you see that the actual range between the best and worst case for the yield maximizing objective you don't have that much of a range in cost. But you have enormous potential gains to be had in the amount of carbon that can be saved. There's a great difference between the best and the worst case. Same for biodiversity loss, and really even bigger for transportation costs. So that tells you that there's a lot of potential for environmental savings without giving up too much on your agricultural objectives. And this graph somewhat highlights that. This is basically a reformulation of those previous bar charts, looking at things in terms of the percent of cost that you avoid when you change the preference that the amount of preference that you take away from yield maximization and assign to the carbon and biodiversity objectives. So you see that in terms of the difference between how much land you need to meet your yield maximizing objective is only 12% difference in the amount of land area relative to the best case scenario. So if you take away just 5%, 10% of the weight given to that objective and give it to carbon and biodiversity protection, you actually get really big gains in both of those two objectives in terms of the amount of avoided cost. And you actually carry along, without assigning any weight to it at all, the objective for minimizing transportation costs, because again, those three objectives are fairly correlated. You have lower carbon near roads because people have already cut down a lot of the trees there. You have lower biodiversity for similar reasons, and you happen to be near roads, so your transportation costs are less. So compromise, a little bit of compromise can buy you a fair bit, assuming this is a valid result. But it does give us some hope that if we actually think a little bit about ecological costs, we can actually have big savings in terms of the amount of damage that's being done. So the problem is there are two major challenges for implementing those types of solutions. The first is getting decision makers to actually buy into that. There's a lot of political reasons that people don't think about these types of things, and economic reasons. So can we convince people to do it? Well, there is some promise. There are agricultural growth areas right now where they have, like there's one in Tanzania, the Southern Agricultural Growth Corridor, where they basically have green development written into part of their charter. So we're trying to get this adopted in that area to see if we can actually help encourage that type of green agricultural development, or greener, I should say. The second major challenge is producing valid results. And that's a big issue. And I'm going to again come back to the dummy data to illustrate why. Okay, so that initial example I showed you was based on artificial data. Let's imagine that's the truth. That's the actual potential yield you can get from growing and the actual ecological cost of those earlier maps I showed. Now here's what happens in practice. We try to estimate those values using a variety of approaches, usually using models and remote sensing and that sort of thing. And inevitably that has error relative to the truth. And this is what you basically get. So on the x-axis now is basically our best estimate of the potential yield and ecological cost. And on the y-axis is the so-called truth. And you can see that there's error around that. Now this error is particularly important for getting to the question of where. Now, I'm taking those two maps again. I have the map created from the truth data and the map created from our best estimates. And I'm going to create the same ranking map and then convert the top 25% of pixels in each case. This is the map based on truth. That's the one I showed you before. This is the one based on our best estimates. And the red pixels are where they agreed that we should convert for new farmland, the most ecologically efficient areas to convert to new farmland. And the green is where they disagree. So they basically only agreed in 3 out of 9 areas. So that tells you that the where question, just a little bit of error in the data, can actually have very big impact on being able to identify low-cost agricultural expansion areas. I should also point out that there's actually not a lot of difference in the mean data, in the mean results between these two data sets. The mean cost-to-yield ratio is only 6% different between those data sets. And then 25th percentile, in other words, the value I'm using to do the cutoff for these, which areas to select, is only 4% different. So a real-world example of where we came across this in our research was a paper that Tim, Dan, and I produced, looking at the larger wet savanna region of Africa. These two maps are two of the inputs that we tested for potential maize yields using two different approaches. One is with a crop model that we ran. The other is actually a data set that Rachel Licker developed, estimating climate potential yields. Notice the differences in potential maize yields on the maps. Okay? We did the same thing with different estimates of carbon potential, and we came up with a carbon loss to yield ratio. The interesting feature is that the mean result, our overall findings for the region were very similar across multiple different variations in these data sets. But we can tell if we tried to identify the best areas to convert, low cost, high benefit areas, that the maps, just looking at these, would be very different. And it's important, the most important thing is to identify where to develop these areas, not how much. So that is this is really why I get back to the point of why data is so critical. We need really high accuracy data to be able to implement these kind of policies. So I'm going to spend the rest of the talk going through why it's so difficult to estimate, to get these types of measurements, how accurate we can be with current generation data sets, and then some of the things we're doing to try really improve the data so we can actually get to implementing these types of policies with some sort of confidence. So this slide illustrates quite nicely why it is difficult to accurately measure, get to the where question. Where are low-cost, high-benefit areas for agricultural development? On the left is a Google Earth image of Iowa, showing cropland in Iowa. On the right is Zambia. As I mentioned before, we are using remote sensing. We have to use remote sensing, particularly over in Africa, because we simply don't have a lot of data about crop productivity, carbon stocks, biodiversity on the ground. So remote sensing is our friend and really the only tool that we can use, combined with simulators. Remote sensing over Africa is very difficult. You get a sense by looking at these maps. This is Zambian cropland. If you could see a bit closer, you can see that this is cropland here. It's geometrically irregular. It's got trees growing in it still, and it's surrounded by, it's not that different from a lot of surrounding vegetation. Compare that to Iowa, geometrically regular, nice clean crop fields and then it's much easier to classify this with remote sensing than it is that. It's got tons of error. And you also look at the average field size, much smaller, so that gives you a resolution problem. When you're trying to do big area analysis, a lot of the satellites we use have a 250 meter pixel size. The crop fields are much smaller than that in many cases. So identifying where agriculture is happening is very difficult. So how accurately can we measure where things are now? So to be able to, we need to get some sense of how confidently we can use our current generation of data to be able to do these types of trade-off models. So I'm going to walk you through some work that we did to quantify this. When I started here with Michael and David as their postdoc, I was working on South Africa and I had the very good fortune of coming up with getting a data set that the South Africans developed, which is very unique, probably for the continents and maybe even for the rest of the world. It's a hand-digitized cropland map. Done by a bunch of people that they hired and trained to basically look at high-res satellite imagery and then delineate the crop field boundaries they saw, each individual crop field boundary. Get a really remarkable data set there, very rich detail that conveys a lot of information, not just about where crops are being grown, but also about average field size, socioeconomics, etc. So I used that map to interrogate the accuracy of the remote sensing products we use to estimate where cropland is in other parts of Africa. And I looked at four major cropland products. The first is South Africa's national land cover product, which is one developed exclusively for South Africa. Second is globe cover, then a MODIS product, and then the current state of the art, which is a map developed by IASA, the GeoWiki map. And then I basically converted everything to a 1 kilometer fractional estimate of cropland, and I subtracted these 4 maps from the really good map that I had for South Africa. And you get, basically, you can see that the areas which are red are basically where these 4 land cover products overestimated the amount of cropland that's there. And the blue is where they underestimated the amount of cropland. And you can see that the map is basically filled with very large overestimates and underestimates. All right. So going one step further, we can take that and calculate the mean absolute error of those overestimates and underestimates. And that gives you a measure of the accuracy that you're likely to experience at any given point on the map. This is now the accuracy of cropland values. And what this is estimating for each of those 4 products that mean absolute error, the measure of the accuracy, as you aggregate the data up to progressively coarser resolutions. So you want to start getting a sense of how much do you have to aggregate the data to have some reasonable confidence that it's giving you a low error rate. So some of these data sets are probably not even worth using at 100 kilometers of aggregation. So that's basically, for context, that's about the current resolution of a general circulation model that we use for climate change assessments. So don't use, globe cover is still got about 15% mean absolute error at that resolution. The South African National Land Cover product that was doing much better. It gets below 10%, after 5 kilometers of aggregation. So this kind of gives you an estimate of the resolution at which you can use the data to make those types of trade-off analyses.
So can you so mean absolute error means that actual percent cropland minus the estimated, or it's the absolute value of that?
It's the absolute value of that.
So it's really hard to get as high as 50% error. Yeah.
That's as high as you get. Yeah. But I'll show you on the carbon map now. So this also matters when you try to estimate downstream error. So I took those maps and I took the IPCC's approach for Tier 1 approach for estimating carbon density, which is where you basically do a paint by numbers approach. For a different land cover type, you assign a different carbon value. There's actually a widely used data set that we in fact used in our Savannah paper that gives you an estimate of how much carbon there is based on what the land cover type is. Is it forest? Is it cropland, etc.? Now I used these maps to basically recreate that map and estimate how much error there is according to what type of land cover is adjacent to the cropland. So if it's forest or not. It's a complicated graphic, but I just want you to focus on those bars there, which is an average of what the error is across a bunch of different land cover types that might be sharing a pixel with cropland. And this shows you how high the mean absolute error is. And the reason it's so high in this case is because it's usually an overestimation error. A lot of these land cover products are underestimating the amount of cropland, therefore overestimating the amount of other vegetation types that might be sharing a pixel with cropland, and therefore they have big overestimates where that land cover type has a much higher carbon density than cropland, like forest does and shrubland, etc. So, in other words, the point of this is that you have really high error rates in downstream analyses based on land cover data as a function of their current accuracy, which is determined here. So the problem is now we want to be conducting these trade-off analyses at sub 1 kilometer resolution or finer for it to be really effective for land use decision making. But we have to aggregate it substantially to beat down error to sufficiently low levels. So that makes identifying valid trade-offs very difficult. So we need new approaches to basically developing the data sets that we're using. And that's what I end up spending a lot of my time doing with other colleagues here. And that's why I'm talking about next generation Earth observation, leveraging some of the new technologies and advances that are happening, both in satellite remote sensing, unmanned aerial vehicles, in-field sensing that Kelly Kaler and Adam Wolf have been developing, using those to get better estimates of both crop productivity but also land cover. I'm going to just focus on a couple of the advances we've made with the land cover side of things to wrap up the talk today. The first is using basically an approach where we take humans to do the mapping for us, but we make use of these big, large global workforces that you can get access to now on crowdsourcing sites, so online job marketplaces like Amazon's Mechanical Turk, where you have a lot of people that are willing to do piece jobs on the internet. So what we did is we developed a platform that allows people to create the same kind of data as the one that I used for South Africa to interrogate the error in the land cover project. So we're having people on the internet develop the same map for us. And so we developed a software platform that allows us to do it. That underpins what we call the Mapping Africa project. We just published a paper that describes the methodology this year. Basically what it does, it looks like this. That's our interface that sits on Amazon's Mechanical Turk website. We serve up a 1 kilometer square sample site to people, and we ask them to map for pay for us what the crop fields that they see in there. And we have, within our system, a fairly detailed accuracy assessment protocol so that we know we're not getting rubbish, but actually good quality. We can, I won't go through that, I won't bore you with the details of how we do it, but basically it gives us a worker-specific accuracy score that we can then attach to the maps that we get and assign some sort of level of confidence to them. And so you can get an output like this, which is the each of those represents the accuracy score, the average accuracy score of an individual worker in a trial that we did, and where 1 is the highest possible accuracy you can get. And this shows sort of this increase in accuracy with experience of mapping assignments. So you actually, we had this on for 24 hours, and we had people that had already mapped 50 to 100 sites for us, and they built up their accuracy pretty quickly. So it's a neat platform. It gives a lot of rich data. Also gives you some insight into how people work online. But you also get some other neat features about this. We've had this offline for a while, trying to build in some new functionality. One of them is the capability to do this, is to have workers repeatedly map the same site so that you can get people's interpretation of what is actually a crop field when you see, when you're looking at a satellite image. We think that being able to do that will allow us to get a better sense than our own expert judgment of what is actually a crop field in an image. So here is basically, you see the fraction of workers agreeing that what's a crop field. Up here, you see everybody agrees because it's red, 100% of worker agreement. Down here, the more complicated site, you have basically a lot more disagreement. Only about 70% of the people map this site. Down here, when you get to smallholder agriculture, much more complicated, it's actually much harder to agree. So you get these really rich data sets. Unfortunately, it's not a very cheap or fast system. You're relying on people to do it. It's slow. You get a lot of workers, it speeds up, but it still costs a lot. So we're paying people roughly about $8 to $10 an hour online to do this for us. It costs, under varying cost models, it might cost as much as $2 million all the way up to $7 million to map all of Africa that way. And it would take, anywhere from 2 years up to about 14 or 15 years doing that.
So it's not actually square kilometers, it's millions of square kilometers?
Yes, correct, yeah. Good point. Yeah, I should label my stuff better. That's in a publication too, so thank you. Wow, okay, that's embarrassing. So, anyway, so another approach that I've contributed to, which is led by Stephanie DeBatz, who's one of Kelly Kaler's students, is this new an automated approach to doing this, a more algorithmic approach that has 3 key ingredients. It takes training data of the sort that our platform is actually designed to collect. It uses new techniques from computer vision that are typically used to figure out what are the individual objects within photos. There's a lot of computer vision devoted to this. and selects features, uses it to select features that then a machine learning classifier, in our case the random forest, can use to make sense of that a ton of different features and give us a better estimate of what is likely to be a crop field and what isn't. So just very quickly through that, we give it some of the data that is starting to be developed, produced in mass by the new generations of commercial satellites that are going up. This is WorldView 2 imagery. It's got very high resolution. It's multispectral, so it's got a lot of information at very high resolution. What we did is we gave our classifier information from both the non-growing season and the growing season for crops to allow it to distinguish better between what's a crop field and what isn't. We passed it training data. That's these sites digitized, as you might do with our crowdsourcing platform. And then the real novelty of it is this randomized quasi-exhaustive feature extraction that comes out of the field of computer vision. We basically just use a lot of simple permutations on moving windows to extract features from the images. Thousands and thousands of features per image, and then we pass that to a machine learning classifier, and then makes sense of that and estimates the posterior probability for what's a crop field and what isn't. So here's the two input data. There's a sub-scene with two inputs. That's growing season on, growing season off. That's our hand digitized labels. And then here's after feature extraction and classification. This is the posterior probability that's estimated of what's a crop field and what isn't. This is a typical sort of smallholder scene. This is over South Africa. This is a commercial agricultural setup. You can see that it has much higher probability. In the commercial setup, it's much clearer. But you also are getting some decent ability to distinguish between crop fields that are less distinct. And so the classifier actually performed pretty well with fairly high accuracy over two types of cropland. Center pivot, which you can't really see it, but there's supposed to be a bar up here. That's the highest accuracy. That stands out like a sore thumb in satellite images. It's a bright green spot. It's a circle. It's very easy to pick up. Rain-fed commercial, clearer boundaries, usually bigger, and also rain-fed subsistence, small fields, noisy, lots of error, and other vegetation images. But in all three cases, you're getting pretty high levels of accuracy. So that's a very promising approach and solving a problem for classification over Africa that's been very hard to solve up until now. So our next step is what we're trying to do is trying to bring these two together in an interactive system where we basically have our crowdsourcing platform connected to the classifier, where they do this sort of iterative training and testing, focusing on areas that the classifier performs most poorly in, and then iterating on that until you achieve an acceptable level of accuracy. So that's where we are. That's one of the ways that we really need to go to develop the type of quality of information that we need to get at these sustainable solutions. I'm talking next generation now because we're now sitting at a time where we're about to have access to a bathtub full of data coming at us every day. This article was just published in the Atlantic Monthly a couple of weeks ago, talking about the possibility in the very near future of us having the Earth mapped at very high resolution on a daily basis. That's a lot of data. And you need new approaches to handle that kind of data, but it offers the possibility of really understanding the planet with more accuracy, much higher resolution than we currently can now. And we need that to be able to implement those types of solutions for making agriculture low cost, much lower cost than it is now. So I hope I've convinced you, that's my talk, I hope I've convinced you without too much boring detail that data are critical for achieving agricultural sustainability, at least in my opinion, and that we're sitting now with the possibility of being able to get those kind of data if we're willing to roll up our sleeves and become data scientists as well as ecologists and policy people, etc. So there's a lot of people involved in this. Some of them are mentioned here, and funders. And so thanks. I'll take any questions.
anyone missed the significance of the middle of the talk when Lyndon proved why the reviewer should not actually accept the paper that we had originally with all the trade-off modeling based on all the inaccuracies in the model. So you will kindly forget the part of the talk that said why not trust our trade-off model. But why don't we have questions now for Lyndon?
So Lyndon, it seemed like a critical part of the conclusion at the start was because there was such a small range in variation in yield within your Zambia example. And then your kind of hypothetical example, you had a huge range of variation in yield. And also in the Africa map, you had kind of an intermediate range of variation.
So the one you saw in the trade-off model is not actually the function of the variation in the yield, it's a function of how the model is structured. Remember, yield is basically the denominator of every term that goes into that model. So the model is, even in the case where you're trying to minimize carbon loss and that sort of thing, it's always finding that it's usually picking out areas that are higher yielding. So it's not the same as randomly selecting anywhere on the map.
Okay, so you still have a lot of variation in yield across Zambia, but you don't have a lot of variation in yield across alternative ways of selecting.
And so that is, so it's very much an agro-centric model at the moment. So agriculture is even implicitly being favored in this. And that's why you have much bigger jumps in the other cost objectives relative to, between the best and worst cases relative to best and worst case for maximizing yield.
Can I ask a follow-up on that?
Sure.
So can you explain a little bit more why the best and worst scenario for the other objective are two? Does it relate to, for example, the spatial heterogeneity across crop, that kind of thing?
Yep.
And I wonder if we apply this rule not to Zambia, but to another region, are we going to see similar results that we can reduce the ecological loss without much reduction on the crop yield, or there should be some prerequisite that this conclusion could help?
I think given the way the model is actually structured, you'd have a similar, a narrower range in the sort of amount of land converted relative to the other costs. It could well be that some of it is that the range in the yields, the way we estimate them, are compressed. But I think it's mostly in the model structure.
It must depend on the covariation of yield.
It also depends on the covariation between those other cost objectives. If you notice that basically everything, the lower cost areas are all basically clustered along roads. So if we had chosen maybe a different measure of, say, biodiversity value, which is less dependent on how close you are to human centers, which are clustered along roads, you might have had a different result.
If all you did was try to say, I want to minimize carbon per hectare, you'd have a totally different result. Or minimize biodiversity impacts per hectare. It's because you say, look, we have to produce a certain amount of food, therefore we need to find areas that have good yields to minimize the amount of land we convert, that you get this convergence. And that actually is the big difference between this model and a lot of other conservation planning exercises, is they don't actually account for the fact you have to produce a certain amount of food.
Yeah, so it's conditioned on the assumption that you have to meet a target, and it always will hit that target.
Do you have any data on land prices in this model at all? Like, it could be that ecological cost was low along the roads, but that's also the prime location for putting housing, industry.
Correct, yeah, no, so one of the things we're proposing to do is actually develop a much better layer for cost than we currently have now. The transportation cost one is very simple, and you need lots of other information like that. No, I don't.
Low transportation costs are very important for the other kinds of land.
Yeah, but it's one cost amongst many, and ideally we'd have like a spatially variable measure of all costs that would go into replace that layer, or maybe even have to write another module. Yeah. So Jacob at the back, and then I'll come back to you guys here.
I was just wondering, you could imagine a scenario, particularly if gradients and cost are shallow, right? Where you feed the model marginally bad data, it estimates a completely different spatial area to develop. Mm-hmm. A solution which doesn't spatially overlap with the optimal hardly at all, but which is barely non-optimal, it's almost as good, right? Or you could imagine that the data that you're feeding the model are leading it to produce dramatically poor planning results. And I'm wondering if you have a sense of which of those is occurring.
So both of those sound like questions related to poor data.
Right, so poor data in your model, you suspect is leading to non-optimal site prioritization, right? And what I'm asking is whether you have a sense of whether it's leading to sort of truly bad prioritizations or prioritizations that are only slightly suboptimal, but in fact, nevertheless don't overlap very much with the optimal prioritization.
That's good. We actually did, well, so to answer the second part of your question first, I didn't show it, but we do some estimates of how much these things actually overlap spatially. So we try to get a sense of that. Relative to the truth, though, what's truly optimal, I don't know. So I have no data to really prove what's truly optimal versus what isn't right now, beyond the data sets that we have. So it needs a lot of validation to be able to demonstrate that this is a realistic concept. So bad data, I think I tried to demonstrate today that bad data does lead to bad results. But how coincident those bad results are with something that might actually be not that bad in practice, I can't really answer. And so, but I can say that we did look at how much our results overlap with areas that are already set aside as farm development blocks, and there wasn't a ton of overlap. So whether that's because the data we gave it are rubbish, particularly like the potential yield estimates, or whether they cited those areas in suboptimal areas. When they made those areas, I don't know. It's hard to say. Yes?
Do you have plans to look at land use for livestock production?
I'm sure Tim does, but the model could theoretically be adapted for that. I am focusing on crops mostly now, mostly because of personally, I think it's the gorilla in the room when it comes to environmental impact.
But in Africa, the vast majority of animal feed is crop residues. They don't have, so there's, you think of bamboo scenes, so here, it's grazing areas, but in most of these, like in Zambia, the overwhelming majority of animal feed will be crop residues. And then there'll be little pieces of grasses that are purposely grown and then harvested. And actually, on all the data, the one thing is absolutely the worst is those purposely grown grasses. Nobody collects data on the area and photos of those, which are very important. So that actually is, we have other projects that are dealing with the livestock elements. But the mapping part is, so the landscapes will be mapped like crazy, right? Like Colombia, which are pasture lands. But in Africa, the mapping of the forage production areas, or in Vietnam, or something. And so actually, even figuring out how to do that, I was actually talking to Lyndon about that the other day. We need to figure out how to do that.
Yeah, it's another thing that has to be modeled basically, and the actual amount of effort that goes into modeling any one crop is actually substantial. It has to be, so you can't really estimate potential yield by just looking at current cropland. You can calibrate a model on current cropland, but then you're basically extrapolating the areas that are not yet farmed yet. So that's a bit more tricky. You have a question?
I'm wondering what has controlled where people have placed cropland in the region to get up to this point. Like if you had perfect data, is it following an ideal maximization principle, or?
Probably not. I think there's a lot of factors that go into determining where people farm. Zambia, one of the places, the things that determines where people farm is things like where tsetse fly is, and also how wet it actually is. So a lot of Zambia is got a lot of good rainfall, but the soils are really leached out and washed out, and need a lot of inputs to actually raise the yield. So people have to practice a very high, the subsistence level, a very high input level of agriculture. You basically have to cut down a bunch of bioma woodland, burn it, that releases enough nutrients to amend the soil so you have a couple of years of fertility. That's a ton of labor. And up in those areas, you can't historically haven't been able to keep livestock for draft planting because sleeping sickness kills the livestock, kills your oxen. So that's like one factor determining a lot of where agriculture is in Zambia now. Then of course you have on top of that colonial history, where the British were, where they set up road networks and infrastructure, that has a big impact. So it's all those types of factors. That is coincident, I believe, without really having great data understanding of that in terms of from a data point of view, with agricultural potential to some degree, but it's certainly not the entire factor.
Let me take two more.
To what extent do you think that LiDAR data would help you reduce the cost of the classification? Because it seems that 3D picture will be quite, will help distinguish agriculture from forest.
LiDAR would certainly be helpful. LiDAR is one of those things that only gets over small areas usually. I remember I was trying to do it for my PhD research. I got asked for a quote for a company to collect LiDAR data for me over Mount Kenya and the Adaires. And they said, about 2 million. So I was like, all right, I'm relying on other data sets. So that's the problem. I think LiDAR is another thing that will become a lot more ubiquitous as the technology advances. But at the moment, I should mention that the carbon data set I used for this analysis is partially based on calibration of a spaceborne LiDAR. And so they calibrated that, they developed a statistical model to relate that to MODIS reflectance, and then they estimated carbon impact. So this is part of that.
Okay, two more questions.
Okay, do you use your model to look at Africa only? Because in your half part, you consider the carbon sink and ecological change, but also if other continents are trying to consider the nutrient cycling impact, because it's only in Africa that the soil is that they does not contain, they don't use enough fertilizer, but in other areas you may consider.
It's a good point. Yeah. So it could be adapted to do something related to nitrogen or other nutrient inputs as well. But at the moment it doesn't. But it's extensible given a bit of programming. So yeah, and of course data. So I'll answer the why I'm not doing that quickly. I'm really concerned about the agricultural extensification issue, the expansion issue in Africa. I've been developing the model. Tim, I think, is motivated by the same reason. Thinking about expansion in Africa. I think intensification has an important role to play, where you start to worry a lot more about the inputs and the ecological impacts of those inputs. But I think relative to a place like the U.S., where that's one of the major issues related to agriculture at the moment, or probably even places in China and India and things like that, I don't think that's going to be the major issue yet in Africa, but I think it will become.
I'm trying to understand the interface with Zambia, all this work.
Oh, yeah.
There's Zambian names on the files. You have to think.
What's that?
No Zambian names on
Actually, 3 Zambian names, and there'll be more. The Zambian Agricultural Research Institute.
So, one of the questions I started with was, what's so important that we got about getting wrong with a given field is a field that turns out not to be a field? Isn't there lots of error correction within the social system?
That's a good question.
And where do the Zambians fit in?
So the Zambians fit in because they've been critical partners in getting a lot of the data that we use so far to develop it and will remain so. And they're critical partners in that, this gets to your social question, we're trying to turn this into an operational tool now. And a key part of operationalizing that is actually working with people, decision makers, in Zambia and also Tanzania where we want to do it. That will basically help us socially correct where the model is. One thing is where the model is giving us rubbish results, so we can then improve it. And then 2, to see whether it's something that they will find useful. And so,
what about the second?
So the second is that I'm finishing up a proposal that's due this week where we're going to try develop it on small areas where they're developing agriculture now in sort of a stakeholder meeting type of framework, in a forum where a bunch of stakeholders come together and we work through the model and use it as a decision support tool to help guide some thinking about how the land use is made.
I mean, we're trying to get part of an iPad and a lower bank. So basically, start getting the tools.
Yeah, so I mean, we could leave it just now where we write nice papers on it and stick it out there in academia land, but ultimately, people like that don't buy it on the ground, and it doesn't really do much good.
Before
Except
everyone
maybe
goes, let's give Lyndon a round of applause.
Yeah, but we're going to first cut down the savannah surrounding
There seems so, I didn't show it, there's some interest in it. There's probably more interest in it there now than there was in, say, in the Midwest.
Draining every weapon. Fine.
When do we want to?
That's great though, that you're
Read over the draft.
Yes, so we could test, for the proof of concept, one of the things we want to check is the impact.
I
of
guess the
the
good thing is,
So that, there's a lot of variables you can test. And I would think there was,
Other than one section.
oh, really? Like technically, what's your proposal?
I've changed that today.
No, but I've
yes,
seen.
and also,
Like,
I think the input in there as well is whether that land is even really just the infrastructure. The land will really be something that's.
The only thing that might be problematic is just
That's another thing, it's somewhat
put the double
cost
axis
of land.
figure together.
That's a way of getting it.
I'm not sure it looks better than single axis. Single axis looks, they track each other better, it's just the price have a higher backstop price.
Yeah.
Other than that, it looks
Actually,
actually,
that's interesting because
Yes.
the ones that you have are wrong.
well, other than that, they track perfectly on the single axis. So maybe we just need to rerun it.
Yes,
So,
yes, you could, or.
I'll show them to you. I'll send you the draft
This
code.
here, but it's too.
Double axis.
It runs with
That's the whole
permutation,
issue. The rest of it,
certainly
yeah, they're identical.
identifying features that
Maybe if you
are
just explicitly
given to
have
it,
that.
uncertain, which could be bad solutions or good solutions that are robust. And so that's another thing that we want to use. It's just like, there's also variables related to climate change. So if this changes in the future, the potential yields, what does it do to that?
Okay.
What's robust?
So you can just note it for like outside of the group.
So that's one of the strengths of it too. It's fairly simple. It's just really, it's all
I
of
think
it.
I'm gonna leave the single axis. It's literally, well, I'll send those.
That's, we would do. In this case, all I was doing was stepping through like 1,700 permutations.
There was no stretching, I literally just laid
That
it
is
back
just proof of
with
concept.
all of
That
them.
for more advanced use, exactly what you say, something like
Same numbers, yeah. Yeah. So the only difference